This is lecture number 2 on modern instrumentation technique subject. So, last class we studied about the error, true value, and percentage of error, limiting error, all those things. So I'm just recapping. So we studied that error, measured value, true value, all these things, and limiting error, relative error. Say limiting error, relative is another name of percentage of error. So and we seen some numerical value and numerical on based on that limiting error and true value measurement values, all those things. So this is the this lecture is the totally based on the theoretical. So various type of error analysis, that is reproducibility, and another name is called as drift, and repeatability. All those things we are going to study today. So this is the repeatability means when you measure the anything, that is measure the current or voltage or power, anything, you will get the some, you will get definitely will get the some error. So in that the repeatability and reproducibility are the two terminology. So the repeatability is you will get the error is the same operator, same setup, and same environment. So that is the definition I given here. The variation that occurs when repeated measurement are made up of the same item absolutely in identical condition, that is same operator, same setup, same environmental condition. So you are taking one instrument, when you take so many times of measurement, you will get the repeated errors, you will get same error you will get, that is called as the repeatability. Exactly opposite, that is called as the reproducibility, the variation that results when different conditions are used to make the measurement. Different condition we are going to take, that is the different operator, different setup, different environment. So that is called as the reproducibility. So that is the difference between the repeatability and reproducibility. And the perfect reproducibility means, actually reproducibility another name is called as drift. So perfect reproducibility means a perfect result you will get, that is we can say as no drift. So this drift is categorized as three categories, that is zero drift and span drift. This also does the sensitivity drift and zonal drift. So these are the categories. So in you coming to the zero drift. Zero drift, you take as this graph, that is here I given one graph, that is the input versus output versus input. So when you plot the graph, the nominal characteristics of the graph is it's passing to the zero. So that is the dotted line I given, that is nominal characteristic, it is passing to the zero. When you take the experiment, basically generally you will get the characteristics of the any experiment. If you take, then you will get the, it should pass the nominal characteristic, that is passing through the zero. When you take the experiment, means some error is occurred in that, so that is not passing to the zero, it is passing through the some values, that is called as the zero drift. That is not passing to the zero, that is called as the zero drift, that is passing to the some other value, that is the solid line I given, that is the characteristic with the zero drift, that is called as the zero drift. This is so this definition, this is happens due to the slippage, permanent magnet setup, warming of the electrical components. So these are the due to its occurs. So why it is not passing through zero means this is the reason for the zero drift. Okay, so then next is the span drift. Span drift is also same thing, but when the span drift the you observe this characteristic, the output versus input you are plotting, the nominally it is passing to the zero. But what will happen when you do the experiment, that is when you do the experiment, that time what will happen, it is not passing through, it is you observe the solid line, it is going very it is not passing to the zero, and it is going the away from the nominal characteristics, so it is going on when the input changes and the output changes, input changes with respect to the output, it changes, it's going on, it's not infinity, it's not stop somewhere. So which is called as zero drift. Okay. uh, so this if there is a proportional changes in the indication all along uh, uh, all along the upward scale, so that is I am saying that it's not a same point, it's going on. If input changing the input, then output also it changes, it's not going to stop infinity, it will going. So it is called as the span drift, the zonal drift. Another is the zonal drift, it is the combination of both the span drift and zero drift. So this is also same thing. It is nominal characteristic is the dotted line you observe, that is and same both will occur in the zonal drift. It is not passing to the zero, and it is not stopping the scale, it is going to it with respect to the input changes, the output is changing, goes on changing. So that is called as the zonal drift. So that is the difference between the all the span drift and zonal drift and zero drift. Zero drift should be the pass to the zero, but in span drift it should is changing with respect to the, it is going on increasing upward scale. So that is the same thing. In zonal drift is the combination of the zero drift and span drift. So that is the thing, this is occurred, this zonal drift is occurred due to the due to the electric and magnetic field, the thermal EMF changing in temperature, mechanical vibration, wear and tear. So this is the cause of the zonal drift. Okay. Then another category is the scale, range and span. The scale, range and span, it is very easy, that if you take the some thermometer calibration between the 0 to 1000 degrees we are calculating. So so then how you define the range, then range is the minimum to maximum we are going to define. See, I written here the x minimum and x minimum to x maximum. So are represented 0 to 1000 degrees. Okay, then are 1000 degrees. So why say 1000 degrees is possible only when the zero measurement, zero, when you start the zero measurement, then only it is possible. So if you take as a 200 to 1000 measurement, then that time it is not we cannot say the 1000 degrees. Okay. So that is the zero range of scale range. The span is the nothing but the x max minus x minimum. So maximum minus minimum. So 1000 is the maximum scale, means full scale deflection value 1000 minus 0, the minimum value is 0. So that is called as 1000 degrees. Suppose suppose you take as one example a thermometer calibration between the 200 to 500 degrees. So then you can decide the range you can say that 200 to 500 degrees we can say, but we cannot say that 500 degrees, because it is measuring from the 200, so it cannot say. The span is the maximum to minimum value. So the span is the nothing but say here I given the range that is 200 to 500 degrees. So the span is the maximum value minus minimum value. So that is 500 minus 200, so that is 300 degrees. This is called as the span. So another terminology in error, the accuracy and precision. The same same, it is very easy. So if you take the scale, that is the 0 to 60 degree 60, see ammeter I am taking, ammeter I am taking. So that is from the 0 to 60 60 amps, amp scale, full amp scale we are taking. So the full scale deflection is the full scale value is the 60 ampere. So when I starting the measurement, see you observe the figure 1. So when I am taking the measurement, so so I'm connecting the instrument as a ammeter to calculate the ammeter of the any circuit. So then I connected the ammeter. So ammeter first, without current flowing, that time it is showing the deflection as the zero value. When the current is flowing into the instrument, then it's showing the 30 degrees. So this instrument is the accuracy and precision. The precision is indicated the instrumentation related things. The accuracy is indicated the which value it is going to show, means 30 amps, 40 amps, the needle going to show, that is called as the accuracy. So suppose the number of times I done the experiment, so uh, some instrumentation damage or something is happened, that time what will happen, you observe the figure 2. So the dotted line you observe, so what will happen, that it is not going to when I'm without flowing the current to the ammeter, it is showing the some 0.5, that needle, the dotted line you observe, so that needle is showing the 0.5 ampere. So that time it is not going to show the zero. When the current is flowing to the that instrument, that ammeter, then it is showing the 30.5. So this instrument is not accurate and also precision. So this is because it is not showing the correct value. So this is called as the parallax error. So I given the definition also. Suppose that an ammeter which possesses the high degree of the precision by virtue of its clearly legible final divided distinct scale and knife edge point with the mirror arrangement to remove the parallax error. See, when you observe the any instrumented in the our lab, so it's having the some mirror is there. So to that mirror is basically used for the error in human error calculation related things. So by observing the that needle point is exactly whatever the measurement of the current or voltage anything is, it is not, it's showing or not. So that is the way of measuring the the system. The same thing, the definition whatever the thing is given, the same definition also I wrote here. uh, so generally the accuracy precision is depend upon the instrument, so and accuracy is depend upon the reading. So that is called, this means the readings are the inaccurate and instrument is as precision as error. So this is called as the accuracy and precision. The next terminology is the sensitivity. Sensitivity is always the instrument should have the sensitivity should be more, because the small changing in the system, the output, small changing in input, the output also changes. This sensitivity we can study in the control system and any control system in maximum. So any equipment should have the, see, if I take the graph, the output versus input, the input is, yeah, suppose I am changing the some input value, then output with respect to is also changing. The definition is also given, the changing in output by changing in input. The sensitivity should always high. So by high means, suppose the small changing in the system, there is a, if your instrument is not not sensitive, so then the mistake errors are more in the system. So that's why the sensitivity is always should be high. So when it changes in the system, then output also should be changed, otherwise error will be increased. So that is then the exactly inverse of sensitivity is called as the deflection factor. So that is given here. So that is the thing. Suppose you take the one example, the Western bridge requires a changes of 7 ohm in the unknown arms of bridge to produce a changes in the deflection of the 3 mm of the galvanometer. Find the sensitivity and deflection factor. See, everything is given. So there is some changes in the some galvanometer. So with respect to that unknown arm of the bridge, so that is the, here we are calculating the sensitivity is the 3 mm by 7 ohm. Then that you will get the inverse of that sensitivity is called as the deflection factor. So that is the thing that is the thing of the sensitivity and the deflection factor. Then another term is called as the non-linearity. So non-linearity, non-linearity, So you observe this graph. The nonlinearity means the you just see this graph. The output versus input we are plotting. Though you first is the ideally it is showing the straight line. Straight line. Ideally it's showing the straight line as this one. Okay. When we are not starting the experiment, ideally the graph was this one. So when the starting the when we start the experiment by joining the different times, different values, you will get different types of experiment you are going to do. So different value you will get. So then ultimately the dotted line of the result you will get. So this is called as a nonlinearity. The nonlinearity is defined as the actual maximum deviation, where the maximum deviation is occurred, that is called as a nonlinearity. So nonlinearity is the definition is the maximum deviation of the output from the straight line by the full scale deflection into 100%. That is called as a so that is called as a non percentage of nonlinearity. So we will see the one example for the nonlinearity. Okay. The histories is next histories also we studied in the transformer. So when the same whatever the study in the transformer same as here also. So where it is the first I am taking histories means first I am taking the I am increasing the input, that is 1 2 3 4, then you will get the dotted line graph. When I am started decreasing the input, then it is not following the same points, it following the another curve, that is the solid line, solid curve I showed is the solid curve. That is the when the input is decreasing means 8 7 6 5 c in this way I decrease it. So it is following the another point, it's not passing to the 0 point. This is phenomena is called as the hysteresis. The hysteresis is the phenomena which gives the different output effect when the loading and unloading of the system. That is the loading and unloading, the same name of as the increasing and decreasing the input or output. So that is called as a hysteresis. This hysteresis is due to the mechanical friction, electrical deformation, elastic deformation, magnetic and thermal effect, and rising and falling of the temperature. This is called as the hysteresis. You studied this one. And another one is the threshold error. Threshold error means, so you observe this one. So if you observe in the I think FET and PGT, you see all this thing. So I am plotting the graph as ID versus and VGS, the gate to the source voltage. So when you increasing the input, there is no change up to VT. There is no change. Where that point we are increasing more input, there where that point start giving the result with respect to the changing the output. So that is called as the threshold point. Here I have indicated the VT is the threshold point. The where that virtue of that point, the first deflection detectable output changes, that is called as the threshold, first detectable output changes. So that is called as if the increasing the instrument input is increasing very gradually from the 0, then there will be the some minimum value change. So that is called as threshold. So where that point is started, that is called as the threshold. Okay. Then the resolution also same thing. The resolution is the same. The input, same. Say suppose you take as this graph, the small measurable input changes. Say output versus input. So there is the first I am changing the input. That is the 2 up to 2 to some x value. It is constant, and some other point it is some point it starts the 2.1, that is it's changing, means when the x value is changing, then that 2.1 is going to change. It means a small measurable input changes. If the input is the slowly increasing from the some arbitrary input values, it will be again be found that the output doesn't change, and at all until the certain increment in the exit instrument is exit. See this definition is given. So that is called as the resolution. The resolution I given the example, one example I given. See this is the one example. The suppose I am taking as the 0 to 200 voltage scale, in that the 100 division is there. So so I want to measure the small changes in the division, means one scale division is I want to measure. See, this is the given the question. The moving coil voltmeter has uniform scale with the hundredth division, and one tenth of a scale division can be estimated with the fair degree. So this is the one scale division. If you calculate, then the total how many full scale deflection, that is the 200. In that, how many division is there? 100. So two first one scale means one indicates the 2 volt, means this is I given the 100 division. So to reach the 200, so one scale is how much? So that is 200 2 voltage, sorry. So resolution is the one tenth of the scale division, so one tenth of into 2, that is the 0.2. So means 0.2 value is required to resolve. This is also called as the error also. This sometimes it's called as the error, limiting error, standard deviation, uncertainty, prejudicial error. So different names it is called. So that is the thing. So and coming to the one example also I given is the instrument measurement a range of 0 to 250 volt with the resolution of the 0.1 percentage of the full scale reading. Then the degree of the smallest changes which can be measured. So he is asking the resolution. So resolution is the see whatever the error we calculate is same as the you calculate. So 0.1 percentage of the full scale deflection 250. So 0.1 by 100 into 250 is equal to the 0.05. So it's required the 0.05 voltage for changing the resolution, means small changing the value. So that is called as the resolution. See, I told that the linearity is I told, non-linearity I told the maximum division by the full scale deflection. So here the question is given, the ammeter has a range of the 0 to 30 amps, means the full scale value is the 30 amps. The instrumentation has the following readings. So see, this here the same thing, whatever the whatever, see, suppose you circuit you are calculating the some current, how much current is flowing in the circuit you are taking. So theoretically we are calculating V is equal to IR, using that formula we are calculating I is equal to V by R. So voltage and resistance is given, different values we are calculating. So that is the current in amperes is showing that is the theoretical calculation. The ampere reading is showing the numerical, means ammeter, by using ammeter we are calculating. So different so current theoretically it's showing the 0, 5, 10, 15 in this way, but in ammeter reading it's showing the 1, 4, 12, 14. So there is the lot of change between the different values and different types different experiment. So 0, 1. So basically the nonlinearity shows that the maximum deviation in the system. So the here given I given here 0 to 1 the maximum deviation is 1, 5 to 4 is the 1, 10 to 12 is the 2, 13 to 14 is the 1, and 20 to 25 is the 2, and 25 to 28 is the maximum deviation is 3. The formula says that the nonlinearity percentage of nonlinearity, the maximum deviation by full scale value into 100%. So maximum deviation is the 3 by 30, full scale value is the 30 into 100. So it is giving the 10%. So nonlinearity is the error in the in the instrumentation based on the nonlinearity, it is giving the 10%. So this is the overall. So the today lecture we learn about the all these things, reproducibility, producibility, all those things, and perfect drift in that zero drift, perfect zero drift, span drift, and zonal drift, all those things we studied, and scale, range, span, and accuracy, precision. So and sensitivity, non-linearity, hysteresis, and threshold. So resolution, all those things in coming classes we studied the in some more errors in the system. Thank you.